Hello guys, in this video we'll be solving Leetcode problem second and fourth of weekly contest 380. Now if you'll see at the problem, the only difference is into the constraints. Okay, here the length of A and B is 10, but in this case the length of A and B is also 10 to the power 5. Okay, now before proceeding, let's read the question. So the question says you will be given a zero index string S, a string A and a string B and an integer K. Now, an index I is beautiful if you are picking up some. I'll just explain it. What does it say? It's complicated to look over here. So it is saying that if you have a string, let's say S, you can cut any string of size a dot length or a dot size. So basically, it is nothing but whatever the string. We'll have three strings S, A and B. First of all, you'll have to cut a string or take out a substring of size A and like whatever the size of A of the we need to cut a string of same length. Let's say it has the starting position I. Now after that we have to cut another substring. It can be anywhere. It can be intersecting or it can be non-intersecting, something like this, or it can be something like this, or it can be completely inside of this. Okay, we have to, let's say we cut from here, or we took out a substring starting from this position J, and this will be of the size B dot size. Whatever the size of B, this will be of B dot size. Now we know that here we took out a substring of length A, and from this J we took out substring of length B. Now, and this should be this, whatever we are taking out from here. Okay, this should be equal to A, and this should be whatever this B length substring should be equal to B. And the difference between this I and J, absolute difference between I and J, should be less than equal to K. In that scenario, this I is called beautiful index. So in our question we need to tell, or we need to return an array that contains all the beautiful indices sorted order. So let's formally see the question. So see, if you'll see that this is saying nothing but you can choose any I such that you'll be able to pick at least a dot length, or that is the at least a substring of size a dot length. Now that's what it is saying, that that should be equal to A, and similarly for this I there should exist an J such that this J, or like starting from this J, you should be able to pick up substring of size of B, and that substring should also be equal to B. And finally this, the difference between I and J should be less than equal to K. So in that scenario this I will be a beautiful index, and we need to return all the beautiful index. Okay, if you'll see this example over here, what we can see, that if A is my and B is a squirrel and K is 15. Now there is only one A, that is from 16 to 17. Here it is my, right? And there is one more here also, we have my. Okay, and now you'll see the index for this my, the index I value will be 16, and for this one I value will be 33. Now for this one, this I, okay, for this I, if we'll see from where we can take out this B, we can take out from this is squirrel, or this is squirrel. Okay, if we take out this one with index 4, like this one, then what will happen? Then the difference is less than t. Okay, so that can be one possible index, or that this I is a beautiful index. Now we could have also taken out this squirrel, it doesn't matter, right? Because anyways this I will be a, this I, like whatever this I will be a beautiful I, or the beautiful index. So it doesn't matter whether this squirrel we take or this squirrel we take. Okay, now for this another my, or like another A substring, if we took this, then what will happen? the starting index or the j value will be nothing but 4, and this I value will be 33, and the difference will be like 29, which is greater than 15. So we cannot take this squirrel, but we definitely can take this squirrel. In this scenario, j value will be 18 and I value is 13. So the difference is less than, or the difference is 15, and we have k as 15, right? So this might will also result in, or like if you select the ith index of this or the index of this m, that will also be a beautiful index. Okay, now how can we solve this problem? So a brute force approach, a brute force approach what can be the brute force approach? Like we can simply go and check, taking out each substring of length a, that okay, is that substring is, or before proceeding in that way, let's say that this is a string s given, right? Now I have two another strings a and b. If let's denote the indices or like the substring which are equal to a, like this one. Okay, and let's consider b something like this one here. Consider that these both are of size b or b dot size, and this three brown boxes are equal to the size of a. Now first of all what we'll have to check, that the index, like if let's say this was index 2, this was index 7, and this was index 13, then for a we can write that this is index 2, 7 and 13. Now similarly for b, let's say it was a 5 and it was 10, and we can say that the starting index where we can take a substring of size b dot size, and that will be equal to b, is 3 and 7. I am repeating what it is representing. So what does it say? That if from the index 2 you take a substring of size of a, that is size a dot size, then that substring will be equal to a. That's what brown box is representing over here. Similarly, if you will take a substring of size a from the seventh index, then also you will get a substring equal to a. Okay, this is nothing but a, this is nothing also but a, and this is nothing but also a, this complete substring. Okay, similarly for b, if we will take a substring of size b dot size from third index, then that substring will be equal to b, that substring will be equal to b. Similarly, another substring starting from the index 10 of size b dot size will be equal to b. Okay, sorry, here it should be 10. I by mistake I have written it 7. Okay, here it should be 10. Now see, if we want this b or this a, because we always know that this I was the index of a, or like the substring which was equal to a, right? So and this I can only be beautiful, right? So if we want this 2 to be beautiful, and let's say there is some value k. Okay, now let's understand this with an example. So let's say if here we have 2, and now if k is 5, what does that mean? What does that mean? That means that another j can be here till 7, or till it can be minus 3. In both the scenario the difference will be 5, but minus 3 is not possible, so we can consider it as 0, something like that. Now if let's say if there are more numbers like 8, 9, 10, many numbers, similarly numbers beyond the 0 as well. So what do you think, best what is the best option we should go for? What is the best option, or which numbers, I should say something like this, which numbers have the highest probability, such that if this is the I, and if I have to select one j, which j will have the highest probability of have giving I minus j less than equals to k, I minus j less than equals to k. It is nothing but the numbers closest to this 2, right? So if we have all the numbers, then what we'll do, we'll just try to find out the numbers closest to 2. So what are those numbers? Number just smaller than 2, or it may be equal to as well. In some cases it can be equal. Similarly, the number just greater than equal to 2. Now see, so 2 was what? 2 was what? Nothing but the index of substring which was equal to I, right? And also in the question we are denoting it with I. And similarly, J was denoted as the index where if we take a substring of B dot length, it will be equal to B. Now, if we'll see this one, if we'll see this one, for every I, what we'll have to select, we have to check if there exists any J. For every I, we have to check if there exists any J, such that mod of I minus J, or the absolute difference between them, or should I write something like this, absolute difference between them should be less than equal to K. Now, if here are many approaches. Two approaches are like, you can use two pointer method to find for each numbers, or an easier or more intuitive way is you can use binary search on this B. Okay, you can use binary search on this B. Let me write it down here again. So let's say if A, or like the I index were nothing but 2 7 13, 2 7 13, and B, or that is Jth index, can be 3 and 10. Okay, 3 and 10. Now now if we want to find the number just closest to, or closest to 2, what can we do? What can we do? We can always find lower bound of 2. Lower bound on which array? On this array. The- we'll talk later like how we are getting these arrays, but for the time being, for the solution, so if we apply the lower bound function, if we apply lower bound function and pass it to, along with, obviously we'll pass like b dot or whatever, let's say it's b indices array. So we'll pass something like this: lower bound b indices dot start, b indices dot end, and then we pass this value to. Then what will it will return? Uh, and also we'll subtract something like this one, b indices dot begin, so that we can get the index. So what will it do? It will do nothing but it will return index. It will return index of the number which is just greater than, let's say if it is returning x, this will be equal to greater than x, or maybe it can be equal to n. It depends. Sometimes it can be equal to n, but if not, then it will be a number which is just greater than equal to 2. So in this scenario, that will be nothing but 10, right? So if we'll do this, that will be, there is no number, sorry, in this scenario will it will be 3, because 3 is just greater than equal to 2. Now we know that at one end, or the number just greater than 2 is 3. Now lower bound always returns number equal to greater than the number which you are passing. That means if it is equal, let's say if 2 was present over here, sorry, let's say if 2 was also in this array of b indices, right, then 2 would have been returned. Now we know that the next number, or there is already a number. If again, if we talk on this number line, and this is 2, we know that there exists a number which is just equal to 2. So I think that will be a better case. But if 2 was not present, what would have happened? We would have now got a number something from here. But there is also a chance that there can be number much closer than this, much closer than 2, in comparison to the distance between the 2 and the next greater number. So in that scenario we have also we have already discussed that we'll have to check both the numbers. I mean, any one of them can be closer to them. So if we'll find lower bound, if it is equal to it, then also it's fine. It will return this number. But if it is not equal to it, it will give the index of this number. So we can simply check with both those numbers. So let's say if its index was 3. So we'll check for less than one index, or not get confused with previous. Let's say it was something like 5. So if we got the index 5 as our answer from this lower bound, then we'll check the absolute difference of whatever number we have passed, that is 2 minus, let's whatever the index we are getting, b index of this, let's say 5, and similarly absolute value of 2 minus b index of 4. Why we are doing this? Because maybe like on a number line again, if this is 2, maybe the next number is we are getting something like this, but the smaller number was 1. So in that scenarios, it is better to take this one instead of taking this 10, right? So that's why we are taking, and of course we'll check like the boundaries whether the number exists or not. Okay, so for this two, we we can check in log n, we can check in log n whether this can be a beautiful index or not. Okay, the only condition is that we have these two arrays. Okay, how we'll get these two arrays, we'll talk about them later, but for the time being I hope this would be clear that we can simply run a binary search over this b indices to see whether this 2 is, whether this 2 is a beautiful index or not. Similarly, for 7, for 13, for every number we can do. So I mean, from this lower bound function, let me write it properly. So we'll have lower bound something like this. Lower bound b indices dot begin, comma b indices dot end, and whatever the value we are passing, let's say a of I. Now we need the indexes, right? Like right now it will return point iterators, but we need indices. So what we'll do, we'll just subtract b indices dot begin. Now so whatever the index, let's say it stored it in value ind. Now we'll check, is it end, is it at the end? I mean, let's say if this was the b array, right, and the value of a was 13, but the maximum value here was 12, so there is no element which is greater than equal to 13. So in that scenario what will return, or the value of this index, let's say index, will be nothing but b dot size. So in that scenario we don't have any number greater than equal to this 13, or we don't have any number on the right of whatever we are looking for. So we cannot take this, we can only use, we can only compare it to the next number if there is any possible, or if there is any present, right? So we'll check if this index is less than b dot size, or b index dot size, sorry, b index dot size, then what we'll do, like for this particular I, let's say we have some answer, okay, or like the current value, something like current initialized to int max. Now we can update this current to something like this: current is equal to minimum of absolute of whatever value we are getting this index, the value at index, that is b index of this index, right, minus I, because that's what the index of a we are using, right, comma this, so whatever the current. Okay, similarly we'll check if 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 we have got any number from in between, then it's fine, we can go backwards and we can check. But if we are, we have got something like this zeroth element, let's say, that is the value of I, a of I, or the, sorry, I mean a indices of I is, let's say, 0, then there will be no number, and the b starts from 1. So we know that there will be no number before this one, so we cannot go on the left and check. So for those scenarios, what will we have a boundary check? If index is greater than 0, then only we'll just repeat the same thing. Okay. So in that we'll have our cur. Then finally checking both the condition, we can check if this cur is less than equal to k. What does that mean? That means we have I and j such that their difference is less than equal to k, and this we already know that this I will come from a of indices Meaning if from this I we take a substring of a dot size, it will be equal to a. And similarly if we take and substring, we take a substring from this jth position of size b dot size, then that substring will be equal to b. So that will fulfill our conditions of the beautiful indices, and this I will be a beautiful index. So in the final answer we can push this I. Okay. Now similarly we can check for all these indices of this I, and we'll have our final answer. So that was one part of the solution. Now the second part, how we can get this indices, how we can get this indices like A indices or B indices, how we can get this. So for that to get the indices, what the question remains is that we have a string S, some big string. Now we have a pattern, some pattern, and we need to find that if like at how many indices this pattern occurs. That's what we are doing, right? Like how many, at how many places. So there can brute force approach in O of n square, O of n cube, but there are various algorithms. One is Rabin-Carr, okay. Another one is KMP, and many more algorithms are, I think one or two algorithms are more, which can help you in finding this position in big O of n, big O of n. Okay, I'll just explain a bit of Rabin-Carr and leave rest of them as an assignment, or like up to you if you want. There are a bunch of tutorials on the YouTube, but if you feel the need, ping me in the comments, I'll explain them as well. So for the time being, let's get an overview of how Rabin-Carr looks like. So in Rabin-Carr, we calculate hashes. Okay. So let's say if we have a pattern something like this, A, B, C. Now, for calculating the hash of any string, what do we have? We have each character as a number. Each character as a number. So we'll start A as 1, B as 2, C as 3 until Z we have 26. Now, for calculating the hash, and not just of this string, like if you want to calculate an hash for any numerical array or anything, what we do, we just multiply with whatever the value we have. Okay, so the value, let's say here array of I multiplied by some base to the power 0 because this is at 0th position, plus again this will be array of 1 multiplied by power 1 position, plus array of 2 multiplied by power 2 b to the power 2 position. And see, this can be very big number, right? So we will take on modulo as well. So let's say we are taking modulo p. So for this scenario what we can do, we can take our base as 31. Why 31? Because we'll have numbers till 26 only. So 31 is a fair base. If you want to read it more about it, you can go learn on the CP algorithms. They have quite explained this rolling hash or this Rabin-Carr algorithm. So what we'll do, we'll take base as 31 and this modulus or PS 10 to the power 9 plus 7, or whatever we say, this 1 in 9 plus 7. So what we'll do for this one pattern, right? For this pattern, if we have pattern A, B, C, what will happen? First of all, the value of A we know that is 1. So 1 multiplied by R base is 31, 31 to the power 0 plus B. So value of B is 2. So it will be 2 multiplied by 32, 31 to the power 2 plus value of C, or let's say instead of C here is it was E. So the value of E is 5. So it will become 5 multiplied by 31 to the power 3 whole modulus 1 in 9 plus 7. 1 in 9 plus 7. This will be in modulo. Okay. Now this is of the pattern. So from the actual string, from the S, like we talked about the pattern, but from the S we know that S is a bigger string, right? But we know that if we want a substring to be equal to this pattern, that must then it must be equal to the size of the pattern. Okay, so what we'll do, we'll take the hash of the first three character. Like in this scenario, we'll take the hash of the first three character. So let's say it was something like D, E, F. Okay, and next character was, let's say, A. So for D, E, F, what will happen? D is nothing but D is nothing but 4, right? So 4 multiplied by 31 to the power, just ignore this modulo part for the now. So 31 to the power 0 plus E is 5, but 5 multiplied by 31 to the power, or let's say let make it B, so don't feel like 4, 5, 6, something like that. So let's say here it is B. So 5 multiplied by 31 to the power 1 plus 2 multiplied by 31 to the power 2. Now we have taken three characters, and here it is G, sorry, or let's say let it A now, A, and then G, P, anything rest of the string. Now we calculate this value. If this value is equal to the hash of the string, we assume that this hashes will be unique. This hashes will be unique. I mean, ideally, there is a chance of 1 upon 10 to the power 9 plus 7, 1 upon 10 to the power 9 plus 7, that they can collide, but it's very rare. So we can assume that they will be unique. Okay, so we calculated the hash of these three characters. We see if they are equal to the hash produced by this pattern, that means we have found one index, whatever index we were here, and at that index, if we will take a substring of the size of the pattern, then it will be equal to the pattern. Okay, now, so if that is equal, then it's well and good. We can simply push that in whatever the vector we want to push it. So let's say if we're checking for A, we can simply put it in A dot indices. Okay, or like if it's a separate function, we can simply push in some vector V, and then finally we can return this vector. Now this is okay if we want to check for this one, but if we'll again go and check for this three characters, so what I'm saying is, if we have D, E, B, G, here it was A, right? P, Q, something like this. First of all, what we did, we check for this one, right? And then if we'll start from checking for this one, and then again we check for this one, and then again we check for this one, what will happen? What will happen? So let's say if it was some bigger number, if it was some bigger number, or like the bigger pattern, then if we'll realize one thing, that let's say if we're checking for the 5 size, then again 5 size. So at each place, or like for each position, what we are doing, we are checking for the 5 length, or like we are calculating the length of 5 characters or a substring of length 5. So overall time complexity will become 5 into n, like almost 5 into n. So if this is bigger enough, like let's say m also 10 to the power 5, like in the second scenario that was the case, right? So if pattern is also very large, then it in that scenario it won't be visible, because the solution will become n square, or that is 10 to the power 10. So that is not possible. So there we have this concept of rolling hash. What we'll do, see carefully. Now earlier, like in this scenario, what we did, we calculated the hash for deb, right? We calculated the hash for deb. Now we need the hash for eba. So so what we can do, we can simply remove this one, or like, or let me write it over here. So we have currently this one, and okay, so we already calculated the hash for this one. We needed hash for this one. So what can we say? That whatever the hash value we have, first of all, let's see. First of all, what we can do, we can calculate, or we can extract the hash value till here, and then we can add the hash over here. Because for this E and B, we know that E value is 5. So if we'll calculate the hash, it will become 5 multiplied by 31 to the power 0. Then B, 2 multiplied by 31 to the power 1. And if, and like as our pattern was of size 3, like in this scenario, then we need to add the hash value of this A, right? So A is 1 multiplied by 32 1 to the power 2. Now, can we get this value of this hash from the previous hash, so that we can save our time? Instead of going n square, we will be able to do it in O of n. Because why? because for each position we are calculating the hash in O of one time, so overall it will take only O of n time. Okay, so yes, we can do that. How? So first of all, see, what we have to do, we'll have to remove this, the value or the value contributed by this, the first character. Okay, if we'll remove this, this will get removed. And then see, initially this E was at second position, then B was at third position. But now, if we start the substring, if we start the substring, or if you want to calculate the hash of this one, we are adding one character at the end and we are removing one character from the front. That means this position of E and B will be decreased by 1. So if it was multiplied by 31 to the power 0 and 2 was multiplied, or this B was multiplied by 31 to the power 2, if after removing this, we will divide it by 31. If we'll divide it by 31, then what will happen? It will become what we need. This 5 multiplied by 31 to the power 0 and 2 multiplied by 31 to the power 1. And we can simply add this value, like 1 multiplied by 31 to the power 2. Similarly, if we want for this G, what we can do, we can remove this one, and then we can divide again by 31, and then we can add for the value of G, that is if A B C D E F G. So A B C D E F G, it will be 6, sorry guys. So it will be 36 multiplied by 31 to the power 2, and rest what it will be, 2 multiplied by 31 to the power 0, plus here it will become 1 into 31 to the power 1. If you'll see from here, that is the correct hash. Okay. Now there will be a bit of complicacy, like if we are dividing it, how will we take into the modulo? That's why I said in itself, Rabin-Karp or KMP is a very big algorithm. Okay, but I hope you would have get an idea. Now let's move to the code. So in this code, see, we have a string, and we have two patterns, right? A and B and this K. So first of all, we have calculated those indices where if we take a substring of size A, that will be equal to A in A indices, and similarly for B, we have B indices. Now, as discussed, we are finding out the indexes using lower bound. If that and using that X, we calculated if whatever the index I we are taking out from the A indices is good or not, is beautiful or not. If that is beautiful, we'll push it into our answer, else we'll ignore it. Okay, and finally we'll return our answer. I have explained you Rabin-Karp or rolling hash in this video, but I have used KMP because it felt a bit easier for me to implement at that time. Okay, but if you want to learn about this, I can explain this as well. Do let me know in the comment section. Now one more thing, in the both the videos I have submitted the same solution, and it's an AC solution. Okay, so yeah, go ahead, try to solve this question, and if you guys have any doubt, let me know in the comment section. Okay, thank you guys, see you in the next video. Let's wait for this. Okay, cool, bye bye.